we discussed in the first hour. Okay, spin will be basically related to the 3 rotations of my particle, but I have a complication which will create some trouble for me because I also want Lorentz invariance. So I cannot work with 3 vectors, I would like to work with 4 vectors. But 4 vectors will in general have a scalar component. So I should somehow get rid of that scalar component if I want to write down a theory of 4 vectors, of spin 1 particles. There will be other problems in our attempts. Let's again go back to the scalar case. In the scalar theory, this was our Lagrangian density. Let's look at the energy density. If you remember, we calculated the energy momentum for vector as derivative of the Lagrangian with respect to del mu phi times del nu phi minus g mu nu times the Lagrangian, which is del mu phi minus g mu nu 1 over 2 del mu phi squared minus 1 over 2 m squared phi squared. Now the energy density is nothing but T00 component, which will give me del 0 phi squared minus 1 over 2 del 0 phi squared minus 1 over 2 gradient of phi squared minus 1 over 2 m squared phi squared, which will be 1 over 2 del 0 phi squared plus gradient of phi squared plus m squared phi squared. This is the energy density. Nice, this is positive. I have positive energies. Well, even if it is negative, I can always shift the energy. If it were negative, I can shift the energy up and down. But the important thing is it is bounded from below. And the minimum I can set to 0. Fine. So let's give it a shot in writing a theory for spin 1, for a 4-vector field. Not phi is just a scalar field. Its values are numbers. Let's write down a field, use a field whose values are 4 vectors. So let me try to write down a theory for a mu. Remember, this mu over here is a dummy index. This is a different mu, it's just the Lorentz index. Well, I should have 4 of them. For each component, I can imagine writing down the corresponding Lagrangian. Nu squared 1 over 2 minus 1 over 2 m squared a nu squared. Okay, this is our first attempt, let's say. I can even put some arbitrary constant in one of them to be determined later on. Let's try to calculate the energy momentum tensor for this thing. You see, the energy momentum tensor in this case will be derivative of the Lagrangian with respect to del mu let's say A alpha del nu A alpha minus G mu nu L. This will be my energy momentum tensor. I'm summing over alpha. I have 4 fields, so I have to sum over all of them, which will be, the first derivative will be del mu A alpha A times del nu A alpha minus G mu nu A over 2 del mu A nu Let me correct my notation. This mu is a different mu.
Am I remembering wrong? Or don't we have some volume integral to have the energy? You know, T00. That's okay.
So no, but if I integrate the density, I get the total energy.
Okay.
Now let me separate my dummy variables from significant variables. So this A over 2 del mu bar A nu bar squared minus 1 over 2 m squared A nu bar squared. The indices with bars are my dummy indices. Without the bar are my explicit indices. So now T00 would be basically 1 over 2 del 0 A times del 0 A alpha squared plus gradient of A alpha for each alpha squared plus m squared A alpha squared over 2. Now I have a problem though. You see, if I would write this, each component of alpha explicitly, I would have A over 2 del 0 A0 squared plus gradient of A0 squared plus m squared over 2 A0 squared minus A over 2 del 0 A squared plus gradient of AI squared minus m squared over 2 A squared. This is definitely not positive definite. Well, you see, even if I try to change the sign of A, let's say, either this term is negative, definitely negative, or this term is definitely negative. I don't get a positive definite energy density. That's a problem. I mean, it's a problem in classical physics. Having an energy that is unbounded from below is problematic in classical physics. It's also it will be problematic in quantum physics. When you quantize them, the problem will be even worse. So it was basically our attempt to write such a Lagrangian device, such a model was too simple. There are other issues. You see, if you look at this model, let's say that I make only the rotation A nu goes to lambda nu mu A mu. I just rotate A mu, nothing else. My theory is still symmetric. So A nu, okay, I try to impose it to transform like a Lorentz vector, or even, well, yeah, any lambda nu mu will do. Even if I take any two of them and rotate them among each other without changing my coordinates. These four fields, they just rotate, even if I rotate them independently of my coordinates, without changing my coordinates, well, it is still a symmetry of my system.
This, when we rotating A mu, there is a partial in the Lagrangian. So lambda does not depend on, partial does not act on
No.
lambda, right? It means somehow it's the global transformation, right?
Yeah, we are only, these lambdas are just constant, so there's no action of the derivatives yet. Or I don't know, if I can just change, I take A nu and multiply it with some different phase. Let's say I take A0, multiply it with some, no, let me not do the phase. These are real fields, so I cannot multiply them with phase. But I mean, the A mu fields just rotate independent of my space, my coordinates. They're not actually Lorentz vectors. And in fact, what I have here is just 4 different scalars. Just the fact that I chose to label them with the Greek letter 0, 1, 2, 3 doesn't make them a vector. At least my theory doesn't tell me that these objects A nu have to be a vector. I would rather have my theory tell it that it's a Lorentz vector. Okay, so those are, well, of course, this is not a big surprise. As I said, we just had a very trivial attempt. Let's try to have a more sophisticated attempt. Let's try to write down the Lagrangian. So how did we write down the Lagrangian to start with? We want to have derivative terms. Remember, the derivative terms corresponds to the kinetic energy. So that we have, those terms are what makes our theory move around, my particle move around. So I want the derivative terms, and I want the square of those derivative terms. Yes, so just look at here. Look at this term. I have the 2 derivatives in a single expression. Those are my kinetic terms. So let me try to write down the most general kinetic term that are consistent with these requirements. It should contain derivatives. It should contain 2 derivatives, in fact. There is one. This is the one that I had written. But there's another one. This term also satisfies all the criteria I require from a kinetic term. It has derivatives. It has 2 derivatives in that term. I don't know what A and B's are yet. And let me also add minus m squared over 2 A mu squared. I'm just looking at such a theory. Now let me write down the equations of motion. The equations of motion I can derive from del mu, derivative of the Lagrangian with respect to del mu A alpha minus derivative of the Lagrangian with respect to del A alpha. This should be equal to 0. I'm just writing the equation of motion for A alpha. By the way, I want my Lagrangian to be invariant under Lorentz transformation. That's the only criteria I have. This Lagrangian that I wrote before, yes, it is invariant under Lorentz transformations, but A mu doesn't have to transform under Lorentz transformation. It can transform independently. That is why that theory doesn't tell me that A nu is a 4 vector.
Does it mean if I have invariant Lagrangian under Lorentz transformation, also invariant under the, also equation of motion is invariant under the Lorentz transformation?
Sure.
Okay.
Covariant.
Covariant.
I want my Lagrangian to be invariant so that the equations of motion will be covariant. Now, if I look at this one, saying that my Lagrangian is Lorentz invariant already tells me that A mu have to transform with in that Lorentz representation because of this term, because the derivative and index of the derivative and the index of my fields, they are coupled there. They have to transform in the same way so that that term remains Lorentz invariant. So this Lagrangian already tells me that A mu has to transform under Lorentz transformations. So already my theory told me that A mu, they transform under Lorentz transformation just like the position. At least that is one achievement, one step at a time. Now, we still have the problem of 4 degrees of freedom. So spin 1 plus spin 0. We might still have the problem that the energy momentum tensor will not be positive. We should check that. Can we guarantee that they will be positive? Let me write down the equations of motion first. That this will be del mu. The derivative of the Lagrangian with respect to del mu A alpha will be just A times del mu A alpha. This is from the first term. Well, from the second term, I will get B times G mu alpha del mu A. No. Let me use this notation, del A. Just a notation. I don't want to use my indices. I'm not basically showing the dummy indices. And this is the first term minus m squared A alpha. This should be equal to 0. This is my equation of motion. Well, let me simplify it slightly. A times the Lambertian acting on A alpha plus B times del alpha del A plus m squared A alpha should be equal to 0. Okay, this is my equation. Let me take the derivative of this expression with respect to x alpha. What I will get, A times the Lambertian acting on del A plus B times the Lambertian acting on del A plus m squared times del A is equal to 0, or A plus B del A plus m squared del A is equal to 0. Well, there is a funny thing that comes from the equations of motion. If A plus B is equal to 0 and m is non-zero for massive particles, del A is equal to 0. Well, that is kind of nice, because remember, the equation of motion, I have the 4 vector has 4 degrees of freedom, but the equation of motion gives me a relation between them. That this condition gives me relates those 4 of them, so all 4 of them are not independent of each other. I only have 3 degrees of freedom left. That was what I wanted.
So
in particular, don't forget, in particular, for example, if I assume that A is a plane wave, a particle with a given momentum, then this equation just becomes PA is equal to 0. This is, remember, this is a massive particle, so I can always go to the reference frame. In the rest frame, sorry. A0 is equal to 0. I am left with just the space components, the 3 vector, which is a spin 1 object.
Can I also have some implication of F mu nu equals 0, so that electromagnetic field all equals 0, and I have only potentials from this,
No.
I equals 0.
Yeah, you see, what is F mu nu? I didn't yet define it. Anyway. So when A plus B is equal to 0, I have my spin 1 system. Well, so my Lagrangian is now, conventionally, what we do is A is minus 1, B is plus 1. Why? Because you see, in this reference frame, it is the space components that I'm interested in. When A is equal to minus 1 in this term, you see, in this term, I have the space components A1, A2, A3 have a positive sign. So that is why I choose a to be minus 1. And then I have the other term plus 1 over 2 del mu a mu squared minus m squared over 2 a mu squared. You see, this term is 0 basically. But I cannot just set it to 0 in my Lagrangian. Because of that term, my equations of motions, if the fields satisfying the equations of motions have del mu a mu equal to 0. If that term is absent, I don't have del mu a mu is equal to 0 from my equations of motion. Now let me write this in a slightly different way. This is minus 1 over 2 del mu a nu squared plus 1 over 2. Now let me first write it explicitly.
It is similar to Lagrange multipliers.
We will come to that later on. You see, Lagrange multiplier is just a constant. I don't have an arbitrary constant here. So there's no Lagrange multiplier here.
It's also, del mu a mu equals 0 is some sort of a gauge fixing?
No. You see, I don't have a gauge symmetry. We will discuss gauge symmetry later on. This theory is not a gauge theory. It doesn't have gauge symmetry.
But there is a.
So massive particles are not gauge bosons. They don't have. If you have a massive boson, it doesn't have gauge symmetry.
Even if I have some, for this, electromagnetic potentials,
I don't have any gauge symmetry here.
Okay.
Nothing. There's no symmetry left.
Okay.
We will discuss gauge symmetry later on. It will appear only if m is equal to 0. But if m is equal to 0, then, well, I don't have this anyway. But this, you see, we will discuss it later on. Here, for a massive particle, I don't have the freedom to choose del mu a mu different from 0. For a massive particle, del mu a mu has to be 0. There's no choice there. So let me first try to write this slightly differently. I will try to change the second term to a form that will be somewhat more familiar, but probably will confuse you even further. This is equal to del mu a mu del nu a nu minus a mu del nu del mu a nu, which is, well, let me keep the first term. I just exchange the derivatives, keeping the total derivatives also in my expression. But remember, total derivatives do not change my Lagrangian. My equations of motion, I can just add any total derivative to my Lagrangian. The action will be invariant. Action will not change, so I can just throw away any total derivatives in my theory. So if I do that, my Lagrangian, I can also write it as, you see, that was my Lagrangian, minus 1 over 2 del mu a nu squared plus 1 over 2 del nu a mu times del mu a nu minus m squared over 2 a mu squared. I just throw away total derivatives. Well, which will be minus 1 over 2 del mu a nu, and what will remain will be del mu a nu minus del nu a mu minus m squared over 2 a mu squared, which will be minus 1 over 4 del mu a nu minus del nu a mu del mu A nu minus del nu A mu. I will define some new quantity f mu nu as del mu A nu minus del nu A mu. In terms of this newly defined quantity, my Lagrangian is minus 1 over 4 f mu nu minus m squared over 2 a mu squared. This is called the proca Lagrangian.
What does it mean, proca?
The name of the guy. You see, the only condition I imposed is that my Lagrangian should describe some spin 1 field. So I wanted my vector field to transform as a Lorentz vector. Furthermore, I should get some additional constraint on the 4 components so that I will have 3 components left. So that those 2 conditions first, allowed me to write my Lagrangian in general in this form. Then requiring that I should get an extra condition on my fields led me to choose A plus B is equal to 0. So that forced del dot A to be 0, reducing my degrees of freedom by 1. And this is the Lagrangian I have at the end of the day. It probably looks familiar, especially the first term, but I didn't use any arguments about gauge symmetries or any other symmetries. I only used Lorentz symmetry. I required a Lorentz vector to describe my field. And I just wanted to reduce the degree of freedom by 1. I'm inevitably led to this Lagrangian. Any questions on this? Well, now let's look at what happens to our energy momentum tensor. What is T mu nu? Now this will be equal to, well, I already wrote down that doesn't change that expression of the energy momentum tensor. This is my energy momentum tensor. So, by the way, could you follow how I went from this step to this one? Basically what I did was, this is antisymmetric under the exchange of mu and nu. So here there's something that is neither symmetric nor antisymmetric under the exchange, but I can always write it as a symmetric part plus the antisymmetric part. But if you multiply a symmetric tensor with an antisymmetric tensor, that is trivially 0. So the only part that remains is the antisymmetric part. And it is this one over here, with an extra 1 over 2. And so my Lagrangian is inevitably written as f mu nu squared minus m squared a squared. Now let's calculate this one. Well, the first derivative is minus 1 over 4 f mu bar minus 1 over 2. Derivative of f mu bar with respect to del mu a alpha times del mu a alpha minus g mu nu. Well, let me just write L. This is minus 1 over 2 f mu bar. This derivative over here will give me a Dirac delta mu bar, Dirac delta. No, the first one is G mu bar mu bar mu bar mu bar Dirac delta nu bar alpha. The second term in the expression of f mu nu, I will get G mu nu bar Kronecker delta mu bar alpha. Well, let me no. Okay. Del nu A alpha minus G mu nu L. Let me move this alpha upward, so that will be the other alpha will come down, but then it becomes the metric. Basically, because I'm raising and lowering using the metric, so metric multiplied by the Kronecker delta will just give me the metric, which will be minus f mu alpha del nu A alpha minus G mu nu L. This is my T mu nu. Energy density is T00, which will be minus F0 I del 0 AI minus my Lagrangian, which is minus 1 over 4 F mu nu minus 1 over 2 m squared a mu squared. Okay, this is my energy momentum tensor. Now we should write it explicitly, but let me use some shortcuts. What is F0I? That's the electric field. EI, Fij, epsilon ijk, fjk, this is Bi. So in particular, for example, I have F mu nu, which will be F0 nu, plus F I nu, F I nu, which will be F0I, because F00 term is 0, plus Fi0, the nu is equal to 0 term, plus Fij, which will be, well, the first two terms are the same. Remember, F0i's are EI. If I lower the index I, if I increase, if I put it upward, I get an extra minus sign. So this is minus E squared. And Fij is whether the I, both I and J is the upper or lower, doesn't make any difference because each brings a minus 1. There are two space indices, minus 1 squared is 1. So each Fij is plus minus some component of the magnetic field. When I'm summing over all Ij, I will be summing over all components. And, well, since I have the F squared, it will be B squared.
John, but the convention that we've used there, it has to be plus for a square, right? Because we say that F0i equals AI, and there.
Remember, F0i is equal to minus F0i.
Okay, then.
Because of that space in one time index.
Also, can I ask? We write it Levitch tensor and the fjk equals bi. If I write it down, that I would write the fjk equals bi aijk. I mean, when I do that, when I want to do that, there is a constant in front of that. you know, I'm just trying, if I try to write it again.
With some constants. Yeah. That constant is 2. Or 1 over 2. It should be 1 over 2, I think. 6.
Is there a problem? I mean, you know, if you write in your notation that if I need the, you know, if I want to put the Levitard tensor on the right hand side of the equation, then I will get some constant, like, you know, because the contraction of the Levitard tensor.
So no problem. Constant is there. Fine. So anyway, let's go back. Epsilon is equal to T00 minus F0I is EI. Del 0 AI plus 1 over 2 B squared minus E squared. And then I have plus 1 over 2 M squared A0 squared minus 1 over 2 M squared A squared. Okay, this is my energy momentum tensor. Well, it still doesn't look so nice. Let me play around a bit. This is EI del 0 AI minus, let's say, EI del 0 AI. I just lowered the index, so that's why I have the minus sign. Let me subtract from this minus del I A0 and add del I A0. Why did I do that? Well, this is F0I, which is EI. Did I miss some signs somewhere? That is why I subtracted that. Let me write it out explicitly. Plus 1 over 2 B squared minus E squared plus 1 over 2 M squared A0 squared minus 1 over 2 M squared A squared. Okay, so I seem to have missed some signs somewhere. Okay, in F mu nu, F mu nu. Okay, this is fine. There's a minus 2 E squared from these two terms. Minus sign is because of this minus sign over there. G00 is 1, so this is plus 1 over 4. So this makes plus 1 over 4 with this factors 2. I get a 1 over 2 B squared minus E squared. Okay, that is fine. Now here I have F0, oh sorry, I forgot that minus sign. There's a minus sign over here already. This is this minus sign over there. So this is plus. Okay, fine. So now you see here I have an EI, I have an EI squared. So that gave me 1 over 2 B squared plus E squared. Well, this is what we would expect also from electromagnets. E squared is the energy density in the electric field, B squared is the energy density in the magnetic field. But then I have other terms, plus del I A0. EI is del 0 AI minus del I A0. And plus 1 over 2 M squared A0 squared minus 1 over 2 M squared A squared. Okay. At least the first term seems to be positive. Well, the other terms, not so positive at the time being. Let me try to simplify write them in a slightly different way. This is minus del I A0, del 0 AI minus del I A0 plus A0 times del 0 del I A0 plus minus the Lambertian acting on A0 plus 1 over 2 m squared A0 squared minus 1 over 2 m squared A squared. Okay, what did I achieve here? Well, this term is a total derivative, so that's not a problem. It will just add a constant to my energy momentum density, energy density. Now, what about the other terms? Let's see what else I can do here. No, sorry, this is del 0 del I. Del I. You see, what I did was I took this derivative, wrote it as a total derivative, and then I acted on this one, A0 times. This A0 is this A0. I'm acting on this factor with del I. That's what I'm doing. If I do that, the first term will be del 0 times del I AI, and then the second term will be the Lambertian operator. Now, del I, remember, del mu A mu, which is del 0 A0 minus del I AI, this is 0. So del I AI by equation of motion is del 0 A0. So this is del 0 A0. Now, another mistake I had here, I don't have the Lambertian, I have the Laplacian. That's the Laplacian. So, combined with these things, well, let me just write it explicitly, 1 over 2 b squared plus e squared. Let me ignore the total derivative. This is the total derivative, I will not write it down. Minus del I something, plus A0 times the Lambertian acting on A0. And plus 1 over 2, well, let me also write it slightly differently, plus m squared acting on A0 minus m squared A0 squared plus 1 over 2 m squared A0 squared minus 1 over 2 m squared A squared. Okay, I have a sign problem somewhere. You say this is equal to 0 by equation of motion. I end up having 1 over 2 b squared plus e squared minus 1 over 2 m squared A0 squared minus 1 over 2 m squared A squared. Okay, I have a sign problem. These terms should be positive, both of them. Well, the easiest guess would be just to set m squared to minus m squared, but that is not something I would like to do. Anyway, these terms should be positive. Let me just look at the sign mistake. Check the book. I will check my computation to see where I made the mistake. But if those are positive, I'm done. Energy momentum density is some positive number plus some constant energy density. That constant, well, I don't care, that's constant. The energy density is now bounded from below. So you see, if I just added 4 fields and treat them as if they are transforming under the Lorentz symmetry, I don't get a energy momentum tensor, energy density, which is bounded from below. But then I drive this proca Lagrangian, and then my new vector field satisfies this condition del dot A is equal to 0. And if I use the equation of motion plus this one, which is also part of my equations of motion, by the way, this I derive from my equations of motion, which gives me a positive energy density that is bounded from below. So my problems that we discussed at the beginning of our discussion of the spin 1 Lagrangian, they are both resolved. I don't know where I missed that science. So any questions? So now I have a well-defined theory. Okay, there are 2 things that we still need to discuss. What happens if m is equal to 0? This is for a massive vector particle, but we have photons, which is a massless vector particle. Then we will see that a massless vector particle has to be a gauge vector. There's an additional symmetry. You see F mu nu. If I change A mu to A mu plus del mu lambda, whatever lambda is, F mu nu will go to del mu A mu plus del nu lambda minus del nu. No, this is nu. A mu plus del mu lambda. But since second derivatives, I can change their order. This term will cancel this one. So F mu nu doesn't change. So I change my field, but my F mu nu doesn't change. That doesn't mean that my theory has this symmetry, by the way. Because A mu squared will go to A mu prime squared, which is not A mu squared. So if my theory has this A mu squared term, my theory doesn't have this gauge symmetry. And the Lagrangian that I derived before, this is the general Lagrangian for a vector particle. If m squared is not 0, it's not a gauge theory. It doesn't have gauge symmetry. If m squared is equal to 0, then it has gauge symmetry. Anyway, we will discuss it next week. So any last questions?
Next week on Monday or Thursday we have presentation.
Okay, on Monday I will have a lecture. We have a lecture also on Monday to make up for the lecture we missed last week. That's it.